Hey Chem students, this is your second lesson in the solutions unit, and this time it's all about concentration. Now if you recall, a concentrated solution is one that has a lot of solute in it. There's a high ratio of solute to solvent. So when we're trying to calculate the concentration of a solution, what I'm really saying is trying to figure out just what that ratio is, how much solute it is that we're talking about in a given amount of solution. So we're going to look at 4 different ways to calculate that concentration. Yes, there will be some math involved, but I'll walk you through it each step of the way. Those 4 different ways that we'll talk about are grams per liter, molarity, percent composition, and parts per million. So those will be 4 different ways that we can represent the concentration of a solution. So in addition to being able to calculate the concentration, you should also be able to, by the end of this lesson, use that concentration to determine the amount of solute or solvent or solution present in a given sample. Okay. Now I'm just going to give you the formulas right off the bat. We're not going to even try to guess through them. We're just going to give them to you straight. All right. So here's our first way to measure, represent, calculate concentration. It's in grams per liter, which is why we have G/L, grams per liter. Okay. To get the concentration in grams per liter, what we do is we take the number of grams of solute, or the mass of the solute, and divide by the liters of total solution. So in other words, if I were looking at a saltwater solution, I would take the number of grams of salt and divide by the liters of salt water. Okay, so very important to keep track not only of the units that we're measuring with, but also what part of the solution we're looking at, whether it's the solute, the solvent, or the whole thing. So in this case, grams of solute over liters of solution. So that's our first way. The second way that we can measure concentration is with something called molarity, and this is a very popular way to represent concentration. Molarity is represented with a capital M, and to calculate the molarity of a solution, we take the number of moles of solute divided by the liters of solution. So you'll notice that these two are really similar. The only difference is that here, instead of looking at the grams of the solute, we're looking at the number of moles of solute. That does mean that you're going to need to be able to do some molar mass conversions, folks. All right. Third way that we can measure concentration is by percent composition, okay? And basically what we're just saying is what percentage of the solution is solute. So like what percentage of a saltwater solution is pure salt. Now to get percent composition, we use this equation. The percent composition over 100, because it is percentage, is equal to the amount of solute over the amount of solution. Now usually we will go with masses there, grams over grams, but you could do liters over liters or moles over moles. It doesn't really matter as long as we're looking at the same measure of both the solute and the solution. Okay. Then the last way that we can measure concentration, again really similar to percent composition, is parts per million, or ppm. Now this is basically the same idea as percent composition, except instead of looking at how many parts out of 100 are solute, now we're looking at how many parts out of 1,000,000 are solute. So in other words, if I were to take a container of salt water and grabbed out 1,000,000 molecules at random, how many of them would be salt as opposed to water? Okay, so to calculate that, we've got this equation. The parts per million over 1,000,000, or 10 to the 6th, is equal to the amount of the solute dissolved divided by the amount of total solution. Okay, so you'll notice that for all of these 4 different ways that we looked at it, it's always some amount of solute divided by some amount of solution. So that's an easy way to remember. It's always solute over solution. Okay. For the rest of this video, we're just going to do some practice problems just to get you nice and comfortable with it. All right. So here's our first one. Calculate the concentration in grams per liter of 11.2. What on earth did I do here? Okay. Calculate the concentration in grams per liter of a solution if 11.2 grams of calcium carbonate is dissolved in 120 milliliters of water. That is full of typos. I will have that fixed on SharePoint for you. Sorry about that. Okay, so to get grams per liter, if you recall back to the equation, to get grams per liter, we need grams of solute and then divide by the liters of solution. Okay, now what you'll notice is we've already got the grams of solute, so we're good to go there. To get liters of solution, what we've currently got is milliliters of solution, so I'm going to need to convert that first. Okay, so I'll convert from milliliters to liters using my good old conversion factor, milliliters on bottom, liters on top, to determine that actually what I've got is 0.12 liters in total of solution. Okay. Now I can go ahead and just plug it into the formula. So my concentration in grams per liter is just 11.2 grams over 0.12 liters to give me a total concentration of 93 grams per liter. That wasn't so bad, right? Let's try another one. Here we know the concentration of a solution. We also know the total volume of that solution. Now what we're trying to do is find the mass of solute. Okay, so what I'm going to do is just plug everything in. Okay, I know the concentration in grams per liter. I know the total volume of my solution. All that's left is to find my grams of solute. So if I multiply both sides of the equation by 0.25, I determine that I've got 0.188 grams of solute. That's it. All right. So that's it for the grams per liter sample calculations. Let's try some molarity ones. Okay. Now here I know I've got 0.800 liters of a 0.500 molar hydrochloric acid solution. I want to figure out how many moles of hydrogen chloride I must have dissolved into this solution. So if you recall, the equation here is that the molarity is equal to the moles of solute divided by the liters of solution. In this situation, I'm trying to find the number of moles of solute, so I'm going to rearrange this equation to find just moles by itself by multiplying both sides by liters. So that's how I got this equation here on the right. The number of moles of solute is equal to the molarity of the solution times the number of liters of solution. Okay. Now I know the molarity of my solution is given to me right here with that capital M giving me that clear signal, and I know the number of liters of solution that I've got there. So now I just plug them in. Okay. And I end up with 0.400 moles of HCl, being sure to take the least number of sig figs. Alright, next up. I've got 0.35 liters of solution. I know that I put 90 grams of sodium chloride into that solution. I want to figure out what the molarity is, what the concentration is in terms of moles per liter. Okay. Now molarity again is moles of solute divided by liters of solution. Now I know what my liters of solution is. I'm trying to solve for my molarity, but I need to plug in my moles of solute, and I don't have that. What I have is grams of solute. So what that means is I've got to do a conversion using molar mass, convert from grams over to moles. So what I do is I put what I know, what's given to me in the problem, on the top, set it up with my grams on the bottom, moles on the top, and then I go looking into the periodic table to get the molar mass of NaCl. That's 58.44 grams per mole. And that tells me that 90 grams of NaCl was the same as 1.54 moles of salt. Okay, so now I know the number of moles of solute. Now I also know the number of liters of solution. So now I'm ready to plug and chug. Okay, so put in my moles of solute on top, my liters of solution on the bottom, and I determined that I've got a total molarity of 0.440 molar salt water solution. Okay. Let's do one more molarity example. Okay. I've got a 0.500 molar solution of hydrogen bromide. I ultimately need 32.5 grams of that hydrogen bromide. Okay, so when this says 0.5 molar solution, that means I've got a little bit of hydrogen bromide in there and a whole bunch of water. I need somehow to extract 32.5 grams of hydrogen bromide. So the question is, how much solution am I going to have to pour out before eventually I hit 32.5 grams? Okay. Now again, my molarity equation is that my molarity is equal to the moles of solute, in this case the HBr, divided by my total number of liters of solution. In this situation, I'm being asked for the volume of the solution, the number of liters of solution, so that's what I need to solve for. So I'm going to rearrange this equation to get the liters by itself on one side. Ultimately, I do that by multiplying both sides by L and dividing by M. So I determined that the liters of solution that I need can be found by taking the number of moles of solute that I need and dividing by the molarity of the solution. Okay, now I've got the molarity of the solution. I know it's 0.500 molar, but I don't know the number of moles of the solution that I need. I don't know the number of moles of HBr that I need. I only know the number of grams that I need. So again, I'm going to have to do another conversion going from grams to moles before I can plug and chug into this equation. Okay. So again, start with the number that's given to me in the problem, 32.5 grams. And then I go ahead and fill in the remainder of my conversion factor, putting grams on the bottom, moles on top, and then putting in my molar mass from the periodic table down next to the grams. When I multiply that through, I determine that if I need 32.5 grams, what that really means is that I need 0.402 moles of hydrogen bromide. Okay, so that's what I'm going to plug in then for the number of moles of solute. I already know the molarity of my solution, so now I'm ready to plug and chug. And once I do that, I determine that I'm going to need to pour out 0.804 liters of solution in order to get out 32.5 grams of just hydrogen bromide by itself. Okay, so that's it for the molarity examples. Now we're going to try some percent composition. Now I know that I've got some hydrogen peroxide. It has a percent composition of 65%. Okay. I pour out 0.750 liters in total of solution, and I want to figure out how much just hydrogen peroxide, just the solute by itself, would I have poured out by doing so. Okay. So let's go ahead and fill in the things that we know at this point. So I know my percent composition, is 65. I know that I have 0.750 liters of solution, and I'm trying to find the amount of solute that's being poured out. So I'm going to plug everything in there, all right? Now in order to get x by itself, I'm going to multiply both sides of this equation by 0.750 liters. Okay. And when I multiply that all through, I determine that by pouring out 0.750 liters of solution, that contains 0.49 liters of just pure hydrogen peroxide with all the water removed. Okay. Now this is a good answer, but the question asked us for milliliters, so I'm going to have to do one last unit conversion just to go from liters over to milliliters. Okay, so I put liters on the bottom, milliliters on the top. There are 1,000 milliliters equal to 1 liter. Multiply it through. So I determined that that means that there are 490 milliliters of pure hydrogen peroxide contained in my 0.750 liters of solution. Next sample problem. Okay. I take 10.0 milliliters of hydrogen bromide to make a 42.5% hydrogen bromide solution. Okay. I want to figure out the total volume of my whole solution. So the hydrogen bromide, if you notice then, is my solute. It's the thing that I am diluting to make a solution. All right. So at this point, I know my percent composition, 42.5. I know the amount of solute that I've used, which is 10 milliliters. I'm trying to figure out the total volume of my whole solution. So let's plug everything into the equation. Okay. So 42.5 over 100, that's equal to 10 milliliters divided by x. Now, in order to get x by itself, right now it's in the denominator. I really don't like that. I really want to get whatever I'm solving for in the numerator as quickly as possible. So to do that, I'm going to cross multiply. I'm going to multiply this numerator by this denominator, and set that equal to this numerator times this denominator. So that means that 42.5x is equal to 10 milliliters times 100. Okay. Then to get x by itself, I'm just going to divide both sides by 42.5 in order to undo this multiplication right there. Okay. Now when I do that, I determine that x, or the amount of solution that I've got in total, is 23.5 milliliters. Okay. Now note that that's the amount of total solution, both solute and solvent. Okay, that's 23.5 milliliters. A bonus question would be how much water is contained in that amount of solution. Okay. Now this is really not difficult as long as you just think it through. So I know that I've got 23.5 milliliters total of solution, that's solute plus solvent. 10 milliliters of that was solute. So to get the amount of solvent, all I have to do is subtract. So of the 23.5 milliliters, 10 milliliters was hydrogen bromide, leaving 13.5 milliliters left that has to be made of water. We'll do one more percent composition problem, and then we'll move on to parts per million, and we'll be done. All right. So last one. We want to make a 5% saltwater solution. We've got 82 grams of water. The question is, how much salt then should I add to that water? All right. So here's what I know. I know my percent composition is 5. I'm trying to find the amount of solute, the amount of salt. Now you might think, I know the amount of solution, that's 82 grams, but what do you notice here? That's 82 grams of water. Water isn't our solution here, it's our solvent. Remember, the solution would be the salt water. Okay, so I have 82 grams of water, the solvent, but that doesn't represent the total mass of solution that I'm going to have. Okay, remember the solution is salt water. So to get the number of grams of solution, what I'm going to have to do is take both the grams of the solvent and add to it the grams of the solute. Okay, so basically in order to get the mass of the salt water, I need to take both the mass of the water plus the mass of the salt and add them together in order to get the mass of the salt water. So here's how I've set that up. I know my percent composition is 5. I'm solving for my amount of solute, or salt, which I'm going to represent by x. Now to represent the mass of the solution, I'm just going to take x, the mass of the salt, plus 82, the mass of the water. Okay, because together the salt plus the water represent the entire solution. Okay. Now again, I'm going to cross multiply this because right now it's icky, it's got fractions, I don't like that, so we're just going to cross multiply. This times this is equal to this times this. I'm going to multiply that through. 5 times parentheses x plus 82 is equal to x times 100. Now, you have to go back to your algebra skills. Here we've got a situation where we've got something being multiplied by the sum of two things. I've got to distribute that 5 out. Yes, I do. Distribute that 5 out. So 5 times x plus 5 times 82. So when I do that, I get 5x plus 410 is equal to the same 100x on this side. Now I'm going to combine like terms. I've got an x term on the left side and I've got an x term on the right side. I don't like that. I want to get them together. So I'm going to move this 5x term over here by subtracting it from both sides. Okay, so that means that 410 is just equal to 95x. And now I can solve for x, the number of grams of salt, just by dividing. And I determined that there's 4.3 grams of salt that I would add to my 82 grams of water to make a 5% saltwater solution. All right, so that's it for percent composition. Let's do a couple parts per million problems and we'll call it a day. So parts per million is often used to measure really small amounts, obviously, because we're dealing with millions of particles at a time. So for example, one place that this is very useful is looking at concentrations of different like ions and minerals and nutrients in our drinking water. Okay, so for example, right here, we might say that the concentration of fluoride ions in our tap water is 0.85 parts per million. So in other words, I know this is kind of weird to think about, but if you pulled out 1 million molecules of tap water, you would expect statistically 0.85 of those molecules, I know it's kind of weird, to be fluoride ions actually. All right. So we know that this is the concentration of fluoride in our tap water in parts per million. Okay. We pull a 7.2 gram sample of tap water. We want to figure out the mass of fluoride. So in other words, I know my parts per million. I know that I've got 7.2 grams of solution. I'm trying to find the amount of solute, the amount of fluoride in that solution. Okay. So we'll just plug everything in. Plug in the parts per million, plug in the amount of solution. We're solving for the grams of fluoride. Okay. To get that by itself, I'm just going to multiply both sides by 7.2 in order to undo this division right here. And when I multiply that through then, I determine that 6.1 times 10 to the negative 6 grams of fluoride would be contained in 7.2 grams of tap water. A little bitty amount, okay? But still, you know, good for you. Good for your teeth. Last sample problem that we're going to go through. If you've made it this far, good work. So now we're trying to figure out the concentration of mercury in a sample of ocean water. Now this is particularly important, especially if you care about our friends in the sea, because obviously a large amount of mercury will be bad for them, not to mention bad for us when we, you know, eventually eat them. So, say we pull out 15 kilograms of ocean water and we determine that that sample contains 3 grams of mercury. We want to figure out the concentration of mercury there in parts per million. Okay. Now, we're trying to find parts per million. We have the amount of solute, which is the mercury here, and we have the amount of the solution, the ocean water. Okay. But before we can plug things in, the immediate thing that I notice is that I've got one thing in grams and one thing in kilograms. That's not going to fly. We've got to have the same units on both top and bottom for parts per million and for percent composition. So what I'm going to do is convert my 15 kilograms into grams so that we're all the same. Okay. So 15 kilograms, I convert that over, kilograms on the bottom, grams on the top. 1,000 grams is equal to 1 kilogram. Multiply it through. So I've got 15,000 grams of ocean water. Now all of my units match up, grams over grams. I'm ready to plug and check. Okay. So my parts per million over 10 to the 6 is equal to 3 grams of mercury divided by 15,000 grams of water, ocean water. To get my parts per million, I'm just going to multiply both sides by 10 to the 6th to undo this division here. Okay. And then just plug it on into my calculator. And what I then get is that the concentration of mercury in this sample of ocean water is 200 parts per million. Or in other words, if I pulled out 1,000,000 grams of water, I would find 200 grams of mercury in that sample. Not so good. Okay. Well, you've made it. We have talked about all 4 ways of representing concentration. There will be lots more time in class to keep practicing with these. Good work, folks. See you soon.